Good morning, everyone. As the convention of the course, let's wait for other students to join for a couple minutes. Good morning, Jen. Oh, by the way, guys, if you haven't installed RobPM or RobGadget, you can spend some time. You can work on that right now. Also, if you can also check the the website's course website's schedule and see the binary that we're gonna play with today. So if you have time right now and if you want to start early, you can work on that now. All right, guys, let's start. First of all, can you guys hear me? And can you guys see the screen?
Yes.
Yes? Awesome. Cool. Thanks for the confirmation. Okay, let's start. And first, let's, talk about logistics. By the way, how are you guys feeling about the first assignment? Sorry, the second assignment. It's done, and I saw many of you are doing great job. So how are you guys feeling? How do you guys think? Do you feel that is easy, is hard, or is like okay, intermediate? It was challenging. I saw you guys typing. Awesome. Yep, I saw yours. Many of you are saying this is hard. And then some of us are saying this is intermediate and this is okay and fun, challenging but fun. I like to hear that. Awesome. Great. Yeah. Yes, 5 was challenging because the way that you work on the CRC one is very different from the others. Cool. So we're gonna have more fun for sure. And it's gonna be more challenging. Hopefully this is not a bad news for you. But I will also try my best to help you understand and explain to you for those different kinds of attack and different kinds of vulnerabilities. So I also want to say that I really encourage you to join the office hour and ask me questions. Even though you don't have questions to ask me, you just can stay over there and watch other people asking questions or showing their concerns. And I do think that that's going to be very helpful. And it will also be very helpful for me to understand, what part of the knowledge that you don't get. Sometimes it's because of you don't get it, but mostly it's because of me not explaining it well enough. So I would like to have this, reaction from you guys so that I know what I should improve and what I should re-emphasize during the class in order to help you understand those important knowledge. Okay, so the first announcement, very important, is that there's going to be no class next week. No class and no video. I want to take a break since you have been working very hard on the assignments. And also it's almost the middle of the semester, so take a break. However, assignment 3 will be released next week. So if you want to take a full break, feel free. But if you still want to work on something and have fun, you can start to work on the third assignment. In terms of office hour, there will not be instructor's office hour. Probably I need to talk with TA. So I will let you know if there's still TA's office hour available, but there will not be office hour for me, and also no videos, and also no Thursday class. Okay, I am sorry, guys. I'm watching the chat. So are there going to be solutions posted for week 3 for the week 3 in class labs? I've actually forgot what week 3's in class labs about. If that is assignment, then we're not going to post any solutions publicly for any assignment, but you can always just come to me and ask me for assignment solutions and I will show you. Like I will when I say I'm show you, that means like there's no document for that. But if you have particular questions for particular challenges, I can help you with that. Yeah, so if you have any questions like Phoebe for those challenges, you can come to the office hour and ask me how to solve. So deadline for assignment 3, yes, it's still TBD because we are. I mean, I don't want to give you guys tough time, but also like I'm deciding. I'm still deciding how long it will be. So by the time that assignment 3 will be posted, you will know the deadline. I think the deadline approximately will be 3 weeks after. So yeah, if I am going to, so I'm gonna release the assignment 3 on next week, and then probably 2 weeks or 3 weeks after the release, you will need to submit assignment 3. It will stop over there. Okay, and then so today we're gonna have a little bit different setup for the course. There'll still be in-class lab, and I will show you the information about this lab. But before you work on it, I will also walk through the ROP and walk through the stack a little bit, so that if you have any questions in terms of ROP, you can just ask me while I presenting those ROP chain and like stack information, present those to you. So first of all, in class lab, so if you have understand ROP very well by yourself, you don't have to wait for me to present ROP chain those information, and you can just work on this in class lab directly by yourself. So the challenge is at same address with the port 6666 since this week is week 6. And then there are 3 binaries that I would like to share with you. The first one is the binary of service. And then the second and the third one are the libraries that this binary is using. So it's using libc 2.31 and with the linker 2.31 as well. So you can download this to dynamic linking libraries from the course website, and then you can just run the binary locally with the environment argument LD preload, so that you'll be able to load the correct dynamic linking libraries instead of the libraries in your own Linux machine. And also you can debug the binary using GDB as long as you set the environment variable correctly. Okay, so this is the information. I am gonna switch to other slides. I'm gonna pretend them. So if you, I would say, like, I encourage you right now, maybe take a screenshot or just like write this somewhere so that you will be able to access this information. If you want to work on this, if you want to work on this by yourself right now, then I'm gonna type the command, the service information in chat as well. Okay. So guys, now I'm gonna swap to slides, and I am going to, first of all, I'm gonna start with reiterating how stack works, especially for function call and the stack frame restoration. And this is gonna be something that I talked about in last week, but I want to talk about this again to remind you and also have a quick recap of what we have learned in past week. Okay, guys, I'm gonna start with Stack Overflow. This is what we have for last week. So this information is very important because in this week and also like the entire assignment 3 is all about Stack. So you wanna make sure that you understand how Stack works properly. That's why I wanna start from here. So first of all, let me talk about stack, how that works. I am gonna use this example to show you how stack works. So here, first of all, let's just assuming that right now we are in function bar and we want to execute full. So we are now at this point. And this is the stack frame for function bar. And actually, if you look at stack, you will be able to find that like for the entire stack, each function will have like its own particular place, and some like there's function bar, function full, or maybe some more, like a part of the stack that belongs to another function, say function main, right? Or even something else. So here, right now, we're just assuming that we are executing function bar and we want to execute full. So that bar is gonna call full. So the first thing, by the time that function bar call full, the first thing it will do is to first save the, put the RIP, save that RIP onto the stack. So here, save the RIP, that particular address is gonna point to the next instruction after calling full. So it will point to the statement of printf, if you look at the source code. And here, and now, we're about to execute function full. In this case, the first instruction is push RBP. So the way that it works is that when I do push RBP, currently RBP is pointing over here, right? And when I do push, it will make that value save over here. And because of the push, the stack RSP will move lower because of push. Okay, and then the next is move RBP RSP, right? And then in this case, RBP's value becomes RSP. So RBP no longer points to this particular place. RBP starts to point to exactly where RSP is pointing to. And then the next is gonna be subtract RSP by fax 50. So RSP is moving down again. And in this way, we form up the stack frame for function full. And those are the locations that are gonna, store the local variables. Okay, I'm gonna write that over here, local variables. Okay, now let's suppose that we have finished this function full and we want to exit function full, go back to function bar. And let's take a look at the stack again and see how stack restore the frame from this RSP to RBP back to originally, like RSP and somewhere RBP, which is the stack frame for function bar. And let's see how this happens. So first, what it's gonna do is that it's gonna have a leave statement. So leave is equivalent to move RSP RBP and pop RBP. Okay, so let's do this again. At this point, before executing leave, here is RSP, the bottom of the stack, and here is RBP, the base of the stack, right? And then the first that we're gonna do is to do leave, and then the first is gonna be equivalent to move RSP RBP. So this is Intel. So we're gonna move the value of RBP to RSP. Originally, RSP is over here. And then after the move statement, RSP value is gonna be equal to RBP. So RSP starts to point to this particular place, which is same as the current RBP's pointing location. Okay, and then the next, which is very interesting, is that we're gonna pop RBP. Okay, let me clear this up. We're gonna look at pop RBP together. So when we do pop RBP, we know that the stack frame is gonna pop something up. So RSP, which points to the bottom of the stack, will move higher, right? So RSP will move to this place. And then because this is the saved RBP value, and this value will be copy paste to RBP, right? So in this case, RSP will point to the place that is above save RBP. And then RBP, because of this restore value moving back to RBP, RBP will point to something that is in a higher location. And then the return instruction will be invoked. And the way that it works is that it will first pop the stack again, and then pop that value to RIP. So you can consider this as a pop RIP. And then it's gonna jump to where RIP points to. And remember that originally we saved that RIP address, which points to printf, the next instruction, followed by function full, right? So in this case, we first pop RIP. RIP's value becomes the same as what has saved in the stack. And then it will jump to where RIP points to. It will execute printf. Okay, this is how stack works for function call and function return. Is there any questions that you'd like to ask? Otherwise, I will move to ROP 10.
I've always never been super clear with why we're using what's going on with pop, besides just removing whatever the argument is.
So the reason why we want to use ROP is because,
Oh, sorry, the pop instruction.
Oh, the pop instruction. What do you mean? That I was trying to understand your question. Is your question is why we're using pop?
Yes.
For function return, or just like in general why we're having this instruction?
I guess in general and in function return.
So in general, this instruction exists is because we want to have this stack for us. Like, when CPU is designed, it has stack such as, so that when they get some location, it will be very easy to get instead of doing the actual memory access. So stack is going to be, so this is the reason why we have a stack data structure inside CPU. And then for stack, the way that the design is, it's it's last in, first out, right? And this is also something similar to a function call, because like usually function call, when A calls B, or in this case, when bar calls full will be the last function, but then full will always be the first function that will finish. So that's why we want to have a stack to, use stack to manage those informations regarding function full. And then for function return, the reason why it uses pop is because, it wants to save the return address. I guess the reason, I guess what you're really asking is why we're gonna save RIP over here and use pop to restore the value of RIP. So the reason why we want to save the RIP is because we want to know where that the function should jump to after function full is finished. So we have to record it to somewhere. And we cannot record it to a constant location, because, if a bar calls full and if full it calls another function, then this call, like A calls B and then B calls C, there's like many layers of calling. It has to be saved in different locations, and it has to save in a location that we can always index, we can always find. And that is why it's nice to have a stack, so that we know that, this returned address is very close and it is closely associated with the functions information, making them together so that when we use pop, we can easily direct the location of the saved return address very easily. Okay, any more questions? No? Good. I am going to go to the ROP. All right. You can see the screen, right? Cool. Okay, so now we're gonna talk about ROP. And then the reason why we want to have ROP is because that, you know, there are more and more advanced defense mechanism. And one of the mechanism is W XOR X. So W XOR X really stops us from executing shellcode saved in a stack because the stack itself will no longer be executable. So you cannot put instructions on stack anymore. That's why we want to have ROP, because instead of putting the actual instructions on stack, we're gonna reusing instructions from code. And the way that we redirect the program to execute the instructions that we want is to abusing the saved RIP register, the saved RIP value in stack. So that's the high level idea for ROP. So we want to abuse the code and then we want to redirect the code, redirect the RIP, redirect the execution of the program to somewhere that we specified in stack. So this is an image of, like the virtual memory map. If you look at a process, and you see that there are many codes that are available over there, right? So there are many code segments. So we can reuse the code inside those code segments as long as we tell the program where to jump to and where to execute. Okay. So here, this is, again, I think this is nice because we just talked about this, and let's do a quick recap. So before function return, RSP is pointing to somewhere over here, like it's like between saved RBP and saved RIP, right? And then when we do return, we're gonna pop RSP and then pop that value to RIP. And then we then will jump to RIP, which is the instruction that RIP is pointing to. So in this case, before and after return, we see that the stack got changed by the bottom of the stack in a way that the bottom of the stack, which is RSP, moving higher. That's because RIP the stack got popped and then the value moved to RIP. So, sorry. So now let's look at another scenario. If we're gonna do return for twice, what will happen? So in the first time, suppose we're at this point, we're before the first return, RSP is the bottom of the stack again, and it points to the saved RIP, right? And then after the first return, RSP moved higher, RIP got restored. And if we are doing return again, right after the first return, what will happen is that RSP will move higher again, right? And then the value that are stored over here, like right higher right next to RIP will be moved to register RIP again. I am checking the chat and question. So I got a question asking, why is RBP not above RSP in the leftmost stack? So this is because we already done the move RBP, like restore the RBP's value to the call stack that is, the call stack of the caller function instead of the callee function. So if you look at the slides of last week, and this is the particular layout for RBP and RSP when instruction return is called and instruction leave has been finished. So leave is equal to, move RSP, RBP, and pop RBP. So RBP's value has been restored. That is why RBP is now has been, like pointing to a higher address. And here RBP is pointing to RBP, which is the callee's base pointer. Okay, so here, let's take a look at this particular part. Let's take a look at, the RIPs accumulating together because of to return instruction. So if we want to make the program to return twice, we have, or say if the program is gonna return twice, then we need to put these two RIPs, like the saved return address all together. If we want to make the first return go to this particular address, RIP, and then make the second return goes to the saved RIP2 address. And in this way, we can construct a chain that execute what we want. So if we point to the first RIP, save the RIP to somewhere like, instruction, move hello to RDI. And we want to, and then the function, after the function returns, the program will execute these two instructions, the move instruction followed by return, right? So if we have these two instructions, we point over here, the program jumps over here, and then the program is gonna return. And remember, when it returns, what it really does is pop RSP. So RSP move higher, and then this address will be stored to RIP. And if we are making this particular address points to a call printf, in this case, we will be able to call printf with the argument of RDI equal to the address with a string hello. So it will print the it will print the string hello. So in this case, we put a chain over here. The first RIP points to this part of the code snippet, and the second RIP points to this part of the snippet. And now let's come up. Yes.
Sorry to interrupt. I just wanted to understand everything. I kind of got the general idea of how the stack seems to work, but the small nuances such as where RSP needs to point while at a certain command is where I'm a bit confused. So can you go back to the how stack works slide, if that's all right?
This one?
No,
you mean,
no, yeah.
Okay, yeah, but give me a second, because that is, another slide. Yes.
Yeah. So over here, while executing in bar, so we have a call to foo, and it basically increments RSP to save RIP, and then it saves the current stack's RBP, and both RSP and RBP point to saved RBP,
right,
while the call to foo happens. And a new stack is created, which is also pointed by RSP and RBP, right?
Yes.
Okay. So in this case, it will just store the local variables, and
Mm-hmm.
when it's returning back, it
Mm-hmm.
will pop the RBP which is saved.
Um, yes, it will pop
And
RBP. Yes,
all right, and RBP goes all the way down
yes,
to its previous address.
yes, exactly.
Okay, got it. And while going back to the training of returns,
Hold on. Yes.
yes, so this is where I'm a bit confused.
Mm-hmm.
So let's assume in the first stack, this is representing a function foo.
Mm-hmm.
So um, it's making a call to bar. So it's
Mm-hmm.
going to save its RBP and
You said it's returning to bar, right? Like it's returning.
it's returning to bar. So
Yes,
it's going to pop RBP and it's going to restore its
exactly.
previous stack.
Yes,
And
yes. And this is the part, like this is the stack that is already popped RBP. So that's why RBP is already, has the previous value, which is the value that is in bar.
then it gets the instruction pointer.
Yes.
And yes, so in the third stack, right, it's again having a return
Mm-hmm.
in it. So
Yes.
bar is returning to let's say XYZ.
Oh, no,
Um,
this is not the case. So
uh,
right now, what I'm just showing is that what if there is a return right after this return? Like in a normal program, this won't happen. You won't have two returns together. Let's
okay.
say that if there is two returns that are having, like they are consecutive. And what will
Um,
happen is, in this case, then looking at the stack, RSP will going higher again, popping another value, and then save that value to RIP.
so how would the pop happen in the third stack's case? I mean, yes, I get that the return is there, but it needs an RBP as well, right, to know which stack to restore back to.
In this
Wouldn't it?
case, this is like this is not like a normal program. This is not a
Okay.
function that it will like restore RBP. I'm just talking about a specific, like imagine a scenario. This is not a normal function. This is definitely an abusing the stack, abusing the function. So we're not really restoring the stack. We're not restoring RBP, but just imagine that there are two functions, there are two instructions, return, and what will happen if return, these two instructions are executed next to each other, and the stack will happen in this case.
Okay, so but wouldn't return internally be hardwired to pop two addresses of the stack? I mean,
No,
assuming one being RBP and one being this return address.
oh, no. So return is only pop one. So
Okay.
return is pop RIP and then jump RIP. And those like pop RBP, that part belongs to leave. That is another instruction, not return.
Oh, okay, got it.
Yep. This is nice
Interesting.
question. Sure. Good question. All right. And then, so, and then I got questions from chat. So this is the case that two returns, but it's not really like in the same function. At this point, let's not think about function, because at this point, the reason why I'm bringing this up is because suppose that we're writing a gadget, we're writing a ROP gadget, we don't care functions anymore. We want to let the program to execute as what we want, not like the function's intention. And I have never seen a function that has two returns next to each other, so I don't think this will happen. But for us, we may want to have something that we want to chain them together so that it will fulfill what we want to do. Okay, and then, this is exactly what I'm saying at this point. Like if what I want to do is to print something, like say to print a message of hello, then what I could do is that by the time that a function return, I make this RIP value points to a particular location of the code, which will move RDI, which will move hello to RDI, and then that code will do return again, right? And then because of that return, RSP will be popped again. The value of RIP will equal to RIP2, and I will make that value points to instruction called printf. So in this case, I will be able to call printf with the correct argument. And then similarly, suppose in this case, I don't want to only print something. I want to do a more malicious thing, such as to execute, to open the shell, to do XCCV bin sh. So if I want to make this happen, suppose that I already overwrite, the stack, and I can just put whatever value for those like saved RIP, saved RIP2. I can put the value that I want. Then the question is how I should construct this part of the buffer so that the program will execute execv with the correct argument. And in order to make this execute correctly, you need to make RAX equal to hex3b, RDI points to the string /bin/sh, and then RDI equal to 0 and RDX equal to 0. And yes, we still need to manipulate the saved RIP. And so I got a question asking that if we need to manipulate the saved RIP, do we still need to deal with ASLR and the canary? And the answer is yes, we still need to handle it. And here, what I am showing is only like for ROP. What I'm showing is only the part of how to not use shellcode, how to not write instructions in shellcode in order to make, like getting a shell, like, calling bin sh happen. So you still need to handle SLR and canary. Okay, so next, let's think about this. How are we gonna make this happen? If we are going to construct, the stack so that it will be able to execute bin sh with all those, registers correct. All right, so I am going to show you one way one way to do it, and this is not the only way to do it. So what I could do is that, like after this saved RBP, it's gonna be the saved RIP, and that is, the original shellcode location, and also that was the, like the function log function record that we had before in last time's lab. So this time, I'm not gonna overwrite the RIP to a function pointer such as record or the address of shellcode. But instead, what I'm gonna do is I'm gonna overwrite the saved RIP, which is here, to the address of the instruction that does pop RAX and return. So let's think about this together. If we're doing this, then after the function, vulnerable function returns, RIP will become this place, and the program will execute pop RAX. And then RSP will point to here, which is like next after the popped RIP, right? And then let's continue. After it will execute pop RAX. In this case, is gonna unstack again, because we're gonna pop this value up and then move that value to RAX. Oops, sorry. After that, RSP will move higher again, right? And then we're gonna do return. And for return, as I mentioned, RSP is gonna move up, and then the value will be stored to RIP, and then it will jump to the location that RIP points to. So in this case, it will start to execute another piece of a code. And let's suppose that piece of a code is doing pop RDI followed by return. Okay, and now let's continue. The next is gonna be, The next is gonna be pop RDI, right? So for pop RDI, RSP is gonna move up again, and RDI will have the value that points to bin sh. So in this case, RSP will move to here. And then we're gonna do return again, right? In this case, RSP gonna keep moving up after return. And then RIP will do move, say RSI 0, and then return again. In this case, this is not pop, so it will just like use this move instruction, and RSI will be equal to 0. And then return again. So RSP will move up again, and then it will go to another snip of a code, which is move RDX 0. And then return again. We come back, RSP move higher again. RIP is going to point to the instruction of syscall. And by the time that RIP calls syscall, we already have RAX equal to hex3b, RDI equal to the address of bin sh, and then RSI equal to 0, and RDX equal to 0. So in this way, we chain everything together using the return instruction. And this is exactly why we call this return-oriented programming.
I have a question on this.
Yes.
So how does RAX already have the value of hex 3b, or are we assigning it? And
we
if
are
we're
assigning it. We are assigning it. And the way that we assign it is to use pop RAX. So here, when you do pop RAX, you're going to move some value to RAX, right? And then the way that it works is you're going to pop the value from stack and then move that value to RAX.
Oh, okay, okay.
Yeah, and this is why, like, between these two, code or instruction pointer, I insert a value in the middle, which is because I want to make RAX equal to some value that I can control.
And does pop also work for strings, or do you have to use like load effective address with
pop works for, yeah. So here, in this case, I am not storing bin sh over here. What I'm doing is I'm having, you see, this is the address. So it's like here, probably it's gonna be in an address. Say this is the address of FF something, say FFAB. And then that is gonna point to the actual string of bin sh.
Oh, so it's a pointer.
Yes, it's a pointer.
Okay.
Yep. And then later on, I will talk about, how to search those, how to find those, like the address of pop RAX, the address of, string being sh. I will talk about that later. All right. Any more questions? So should there be a 0 on the stack after pop of that? Yes, if you're using pop RDI. So here, oh, not pop RDI, because, give me a second, let me understand your question again. So the question is, should there be a 0 on the stack after pop RDI, like there is for pop RAX? So here, the answer is no, because for RDI, what we want is the value of, pointer being sh. So that's why we put the pointer after pop RDI. In this case, when we do pop, the pointer of being sh will be copy paste to register RDI. And then for the rest, like this part, the reason why we don't put like 0, because here we're using a move statement instead of pop. So if this particular instruction is doing move RSI 0, then we don't have to pop anything from the stack. We can already get the value of RDI, assign the value 0 to RSI directly using this particular gadget. So the interesting for gadget is that, you can customize it. You can decide what instruction that you want to use in order to, like make RAX is equal to 3B, make whatever condition satisfied. And here I'm only showing you one possible way. Like in this way, I'm using pop RAX. You can also try to find if there is an instruction that is directly doing move RAX hex 3B. If that works, you don't have to have pop RAX. And similarly, I can also just, instead of using move RSI 0, I can have pop RSI, and then I insert a 0 after pop RSI so that I can move the value of 0 to register RSI. All right. So that's pretty much for ROP chain. I got more questions. So why do we want the value hex 3B in RAX? This is because of function XCV, XCVE. So for this particular function, it needs to, this is a system call. And for system call, you need to have a signal. You need to have this specific code to, to tell system call that you are calling EXECVE instead of other system call. Okay. All right, guys. I am, again, this is in class lab. And then now I'm gonna give you some time to download it and then try to run it. And meanwhile, I'm gonna handle the other questions. So hex 3B is EXECV, is not, hex 3B is not EXECV for all systems. And if you want to get those information, you could just, search system call and then check, say, x86 or x86 64, and then you will be able to know, what are the value of RAX or EAX associated with a particular system call. So to decide whether or not I use, whether to use pop or move, the way that I decided is usually depends on the gadget. So I will use tools such as ROP gadget or ROPM to search that instruction or those code snippet from the binary or the library. And if I can find it move RAX hex 3B, I'll just use it directly, because in that way I don't have to change, I don't have to put some actual value on the stack. But if there is no such, move statement with the particular value that I want, I will have to create the value by myself, which is to use pop instruction. All right, guys. We don't have too much time to work on the ROP, but I will try my best to squeeze everything in this video. And if you have questions, you can ask me, in Slack. And also, I am going to share the tag code with you later on, so that even though you don't know what's going on, you can always just like play the code and try to understand it using GDB by yourself.
Is the binary stack that we're using, and then the
Yes.
libraries are the, okay.
Yes, exactly. All right, guys, I'm gonna stop sharing and create a new sharing in my Linux machine. All right. So suppose let's work on this challenge together. And first of all, let's try to understand what is code, like what does this code is trying to do. Let me open Ghidra. All right. And let me create a new project. Import a new file, which is stack. And after the big dragon digested the binary, we're gonna start. Yep. First time, let's just let it roll. Okay. And again, let's start from main and see what's going on. Okay, so here's the main function. Also, you can connect to the server and you will be able to see, the information dynamically. So basically, it will call function check. And then if function check returns 0, then your participation is not logged. And then if check is returned 1, then your participation is logged. And let's take a look at the check. Here it says that welcome to week 6, and then it will ask you to type your SU rate to check your participation, right? And after that, things become a little messy. So it has a get, and then it gets to local variable. It gets the value, so it gets the string, read that from standard in, and then it stores in local 48. So actually you see, like local 48 is supposed to be a character string. So it's supposed to be a string. Let's retype it. Let's make it start for now. All right, after change that, it looks slightly better now. And then after we get the string, it first get the string length of the string. So this is actually the string length, right? Let me rename it to make it look nicer. And then it will malloc something, right? And then it will malloc with that particular size. It will malloc something to dest. And then what is this information? This looks pretty, like it's very specific. So we want to change that. Okay, so it's like, it's some records, right? Let me see if it can convert that to something else. Okay, so this destination, also you see that because of those strings that are copy paste destination, we know the destination should also be a string. And then let's change the type. Make it to char. We type it. Oh, that's not a problem. And then also let's rename it to destination. Looks better. And also, so here there's a stern and cat. So we want to copy paste from this value to dest. And let me rename this as well. We call it source. Okay, and then what it does is it's gonna check the value, checking dest, right? So it prints something. It prints that it's gonna checking this particular string, and then it's gonna use access to check if this path exists. And if this path exists, it's gonna return 1. And then if it's if the path doesn't exist, it will return 0. So can someone tell me that what is the vulnerability for this particular function check?
Well, the gets function looks pretty interesting.
Yes, exactly. The gets function looks pretty interesting, or say pretty suspicious, right? Because there's no size specified for argument source, for argument src, and it may be able to overflow something. Then let's take a look at src. So src lives in rbp minus hex 40, right? Because here we can see that after we call get, we're gonna get the address of SRC, and then the address, oops, sorry. The argument of get should be, the first argument stores in RDI, and then RDI comes from RAX, and then RAX comes from the address of, RBP minus hex 40, because this is LEA, right? So it's like load the effective address of this place to RAX, which is equivalent to RAX is equal to RBP minus hex 40. This is exactly something that we had for our reverse engineering assignment. Cool. All right, so now we know that the address of, let me put a comment. Oh, comment. Here is SRC is RBP minus hex 40. Why did it show? Let me do this again. Okay. So what we want to do is to leverage argument SRC so that we can overwrite the return address of check, and then we use ROP10 to redirect it to something that we want. In this case, what we could do is we are going to use, execve bash /bin/sh to get a shell. Okay. So now we already have this code, and now let's write the code together. I'm gonna swap back to, okay. So let's do, say, attack demo.py. So the first thing that I always do is that I want to make sure that I can run this binary with the correct library locally, so that I can debug and I can figure out what's going on with this specific binary. So what you could do is, by the way, this is not very well Python behavior. You probably want to specify it, but you can specify in the end after you know the complete set of functions or argument that you want to use from a particular package. Okay, so again, come to main. So I want to be able to run this locally, and then I'm going to use process coming from pawn. And then I can do, the first argument is going to be the binary. And then I want to specify the environment, because I want to load the correct library. I'm typing one more bracket. And then we can try this. Let's just do p-dot receive line. All right, so let's try this for now. I'm gonna try this from another site. So it works. It says that it starts the process, and then it prints the first message coming from the process. Okay, so the next is that we know the vulnerability already. So, and we know that we need to overwrite to get the, to get the return, overwrite the return address. We need to overwrite the buffer itself. It's from RBP. The buffer from, the buffer's address is RBP minus, vulnerable buffer is RBP minus hex 40, right? And then we know that the saved RIP is always at RBP plus 8, right? So here we need to have a padding which is equal to hex 40 plus hex 8, which is 72. So we want to have a padding with the length of 72 in order to overwrite the return address. And then here, let's do a check stack first for this binary so that we know what has been turned on and what is not turned on for this binary. Okay, so this particular binary, there's no stack canary. So we don't have to bypass stack canary. And then we know that there is no PIE. That means that this binary will always load from this address. And then, but it has NX enable. So that means that you cannot put shellcode over there because the shellcode, since it's in stack, will not be able to execute it. That's why we need to use ROP. And then the next that we want to do is, we want to create a ROP. And remember that we need to do, to use exec. And I'm going to copy paste the exec's required condition. So for execve binsh, we want to do, which is rax has to be equal to 3b, and then rdi has to be equal to a function pointer, it's a pointer that points to sh, and then rsi has to be equal to 0, and then rdx has to be equal to 0. Okay. So now how to get this work? We have to find those, gadgets that can make this work. But suppose that we can't find those gadgets. And then now let's just start to think about how to come up with the ROP chain that will pull all those together. So suppose we call it shell. And then if we want to have this chain, we have to use, let's just call it attack. We have to start with this padding, right? Which is, 72 bytes. And then we could use find a gadget that would do RDI. And then let's try to find the address of binsh. And then we'll have to pop RSI. And then we can just put the value of 0 over here. And then let me continue. And we can continue to have, we want to make RD access equal to 0. If we can find a gadget that can directly move RDX, directly move 0 to RDX, and then we do pop RAX, and then we want to put the value of 3B. And then we want to do syscall. All right. So now the next is how we're going to find those values, right? And the way that we find this value is to use ROP gadget or ROPium. So for example, if I want to find an address that has bin sh, like a string of bin sh, and I want to be able to locate the address of string bin sh, I can use ROP gadget. And if you just do help, you can find that this is already here. Like these are some examples, and this is one way to find bin sh from a binary. I would also use the string. I feel the string is slightly better. Actually, there's really not too much difference. So the way that I find is I'm going to do ROP gadget by the binary. But I know that the binary itself may not have something interesting. I can try it first, binary, and then string sh, and it shows nothing, right? But that's okay. We can try the other two dynamic linking libraries and see if we can find this string. So now let's try ld. Still no such string. Let's try libc. Nice. We found that there is a particular address that is associated with bin sh. And now we need to remember this address. So I will put here address bin sh is equal to 1b7588, and this is hex. And similarly, we can find the other addresses. But then here's another issue. The issue is that after we have this thing, we need to first make sure that those values that we store here is in little endianness, because the binary itself is in little endianness. So the way that to convert that value to a little endianness with the correct byte, with the correct, the big architecture, is that we could do p64. This is a function coming from ponlib, or we could also just use the struct. Here, I'm going to use p64. And similarly, for the other address, we also need to use p64. So in that way, we can put them all together into the ROP chain. And this is not over yet, because if you look at the location, you found that this is the offset of the dynamic linking library. And the library, when it is dynamically linked, it will link to a base address, which is different from 0. It's going to be a base address plus the offset, so that you can get this string. Then the question is how to be able to get the base address. So today, because of the limit of the time, I'm not going to tell you how to get the base address, but instead, I will give you the base address. In future video, probably the video, in the week after next week, I will show you how to get those dynamic linking address and also how dynamic linked functions works. So here, I'm going to put over here, the base is equal to, actually, that's a great question. Let me search for it. Oh, actually, I don't know, but I can run my attack script to find that address.
Is there a pwn tools functionality for getting the base address?
Not exactly, because the base address is really, it's program specific and it's process specific. So there's no unified way to get to the base address, but you have to know how this dynamic linked library is loaded into the process. So that's why you need to use this vulnerability to get the the base address of the dynamic linked libraries. Okay, so it's this. And also the program, there's no ASLR enabled, so the base address will be constant. Okay, so suppose that we already have that. So what we need to do is that we need to have, after padding, we need to add base with the location of pop RDI, the base of the location of the address of BNSH, and all those again, like all those together. P64 again, base plus, etc. And then in this way, you will be able to get a shell. And here I'm gonna just show you the way that I get a shell so that you know that you how will count if you succeed and what you should do after you get a shell. So here, once you get a shell, you will be able to type just like you are connected to the server. And then what you want to do is to do attach records followed by your ID, and you're done. You can exit. Some issue that I cannot exit because of the network that I set up for my Linux machine. But after this, you should be able to exit by yourself, and it will work. And then here, after you are sending those attack, make sure that you do p dot send line the attack, and then you want to do interactive so that you can start to interact with the server with this shell. All right, that's it for today's lab. And I know that this is incomplete, and I will send you a complete version later on. And in next week, or actually in 2 weeks later, we will talk about dynamic linking libraries and how to link that library, how to link the information using a vulnerability. That's pretty much it. I will stop recording and stop sharing.